How's it gang? Welcome back to Math 100. This is 3.4 on the nature of proof. This is the last section of chapter 3. Woo, made it. Okay, so what are we talking about today? We're talking about whether an argument is valid or invalid. You know, in math, really the biggest thing to me in math, the crux of math is really to prove whether something is true or not. And that has a lot to do with logic. It has to do with, are you making logical, valid arguments to prove your thing that you're trying to prove? Or is there a gap in your logic making it an invalid argument? Now, today we're going to focus on evaluating some of the common valid arguments and common invalid arguments and just being able to tell when we're talking about which one, whether we're looking at a valid argument or whether we're looking at an invalid argument. Sometimes it's actually hard to tell. Sometimes we can be tricked. And why do we care about this? Well, we care because if we're trying to convince someone else of something or we're trying to make an argument, we want to be making sure that we're following sound logic. Because if we're not, then everything we say is invalid. And then the flip side, we want to make sure that if someone's trying to convince us of something, that they're following good logic, because we don't want to be convinced of something that's BS, basically, right? Okay, well, let's look at this. What is an argument by definition? An argument consists of two parts. Number one, premises. And premises are what we call the given statements. So when we say given statements, these are statements that we're just taking for granted as being true. Now, it may or may not in reality be true. The premises might not be true, but we're not concerned about that for this purpose right now. We're only focused on the structure of the argument itself. So if we're allowing those premises to be true, is the rest of the argument a valid argument or not? And that's what our focus is on. We're assuming the given statements, we're assuming the premises, we're allowing them to be true every time, but we're just focused on from that point onward, is the argument valid? Okay, so that the premises are the first part of the argument. The second part is the conclusion. The conclusion is the result that's determined by the premises. So it's the result determined by the premises. Now, an argument is valid. Let's use blue for valid anytime we see valid from now on. So an argument is valid if the conclusion is true once the premises are assumed to be true. And we're always going to assume our premises are true for the sake of evaluating arguments. If the conclusion follows, then it's a valid argument. On the flip side, let's see, change colors here. Let's use darker red. On the flip side, an argument is invalid, or we call it a fallacy, if it's not valid. That's pretty straightforward, right? Invalid if it's not valid, of course, right? And then we call that a fallacy. All right, so today we're going to look at 3 common valid arguments and 3 common invalid arguments. And most of these, actually 2/3 of these, come from things that we learned before. The conditional statement, the contrapositive, the converse, and the inverse. And we learned all of those guys last class, right? So hopefully we've got those down. If not, then just go back and review. But if you remember what we talked about last time, recall that the conditional statement, if P then Q, was logically equivalent to the contrapositive statement. And for that reason, we are going to get valid arguments coming out of those two formats. Okay? The ones that were not equivalent to the original conditional statement, remember, were the converse, right? That's when you reverse the order of the left and right. And the inverse. Inverse was when we just negated each side. What did work, what was logically equivalent, was when I did both of those things. I reversed the order and I negated each side. And think of some examples on your own to convince yourself of that being true. Okay, let's look at these now one by one. First thing I do want to notice though, before I continue, is all of these common valid arguments and all of the common invalid arguments, they actually all start the very exact same way. If P then Q. So we're starting with the same exact first initial premise. All 6 cases. If P then Q. Every single time. If P then Q. If P then Q. If P then Q. If P, then Q, if P, then Q, if P, then Q. Every single time, right? Okay, let's undo all this highlighting and let's start from the beginning. We're going to go through these guys one by one. Starting with the simplest case, the direct reasoning case. So like I said, if P, then Q, that's always the same. And what does direct reasoning say? It says, if I start with P on the left and with Q on the right, that's the same argument I'm going to make. P on the left, therefore Q on the right. And oh, by the way, you see these 3 dots right here? That is the symbol for therefore. Okay, that's just shorthand for the word therefore. It's the math symbol for that word. Okay, so anytime you see those 3 dots, remember, therefore, please don't email me asking me what that is because I'm telling you right now. Okay. So what is the pattern, right? We're following the direct reasoning pattern. If you look what's happening here, we've got something on the left, arrow to something on the right. The next premise is the thing on the left, and the conclusion is the thing on the right. Right? So we went from left to right. Basic direct reasoning. Same pattern. You can think of this, if remember, the P's and Q's are not so important. We have something on the left, something on the right. And then the second premise is the thing that was on the left. And then your conclusion, therefore, is whatever is on the right. Now, just to make this a little more concrete, let's use a working P and Q. So I'm going to just make a simple statement. Let's say P from now on, for the purpose of illustration, P is going to be this statement. Today is... it's big day. Today's Sunday. Okay? And then Q is going to be the statement. Tomorrow is Monday. Monday follows Sunday, right? Okay, so how would that translate in this direct reasoning case? So if today is Sunday, then tomorrow is Monday. That's true, right? Okay, so we're assuming that's true anyway. Now, the next premise, today is Sunday. Okay, if today is Sunday, tomorrow's Monday. Today is Sunday, therefore, tomorrow is Monday. That's direct reasoning. Following the same pattern as the original conditional statement. All right, let's look now to the indirect reasoning. So what is indirect reasoning? Again, the same initial... Let's zoom right here. Same initial premise, if P, then Q. Yeah. The second premise is what we get from the contrapositive statement. See that? The contrapositive, remember, if my original statement was if P, then Q, the contrapositive is not Q on the left, not P on the right, right? So that's what you have here. Not Q, therefore not P. Let's break that down in terms of what's on the left and right. Use that same color here. So here, what have I got? I've got something on the left, arrow to something that's on the right. The next part of the pattern is the negation of the right side, therefore negation of the left side. That's the pattern of the contrapositive, right? So when we use that pattern, we can say indirect reasoning. By the way, I also accept, if you say contrapositive, reasoning by the contrapositive, I also accept that as an answer. If you're writing on a test. Okay, let's bring that back to our context. So the original if P then Q, that's again, if today is Sunday, then tomorrow is Monday. I accidentally erased part of my Y there. And then what would this next part be? That's saying tomorrow is not Monday. That's the negation of Q, right? Tomorrow is not Monday. Then therefore today must not be Sunday. Today's not Sunday, because if tomorrow is not Monday, then today is not Sunday. And that makes sense, right? That's true. That's a valid argument. Okay, transitive reasoning. Transitive reasoning goes if P then Q, same original start. And then if Q then R. If you have that pattern, then you can go from the very beginning, if P then R. So that's a natural conclusion. That makes sense, right? Let's just pause and unpack that part first. What you're basically saying is if you go from P, arrow to Q, then you go from Q arrow to R, well, then you could have gone from P all the way straight to R, right? So let's make up a new statement for R. R will be, how about this? Let's use black here. So R will be the statement. Let's unwrite in here. The day after tomorrow is Tuesday. Okay, so what's happening here? You're following, basically, it's translated, right? Because you're going from P to Q to R. Oops. And you're going in the correct direction, following the order of the following direction of the arrow, right? Now, notice that there's actually two valid conclusions that could be made. So I just showed you one of them, right? If P, then R. But there's another one that you get for free. And if you look carefully at the other conclusion that is also transitive reasoning, valid transitive reasoning, that is actually the contrapositive of the first natural valid conclusion, right? So what's the contrapositive if P then R? It would be not R, arrow to not P. So you can conclude either one of those things and be correct. So what would that sound like in context? Let's put it all together. Sorry. Let's put it all together. So this first part, if P then Q, would say, if today is Sunday, then tomorrow is Monday. If tomorrow is Monday, then the day after tomorrow is Tuesday. And then you conclude, if today is if today is Sunday, then the day after tomorrow is Tuesday. That makes sense. Or what's the alternative conclusion? If the day after tomorrow is not Tuesday, then today is not Sunday. Also, that's also makes sense, right? What's the pattern here? There's actually two possible patterns. You're going from left to center, from center to the right. Therefore, the conclusion is left all the way to the right. Oops, squeezing that in there. Sorry, guys. Okay, and for free, or therefore you can go from the negation right to negation left. Why is that? Well, that is just the contrapositive of the most natural conclusion that you could make right there. Okay. I would just take a pause here, guys. Let everything sink in, and maybe as you're going, just pause as much as you need to. I know this is a lot to throw at you right away. I usually don't like to have such a long introduction, but this is just kind of I just want to unpack this as much as possible. So pause here, just let that sink in for a moment. So far, we've done the three valid arguments, the three valid, common valid arguments. We're about to get to the invalid ones. Okay. Before we get to the invalid ones, I do want to say one small comment about the transitive reasoning, though. One thing that could go wrong with this is if the centers don't match up. So you see, this is P to Q. If this was something else other than Q, if these guys don't match up perfectly, then the whole thing is not going to work. It's not going to be transitive reasoning anymore. It will probably be a false chain. If it resembles transitive reasoning, but it's not quite, then that's what we call a false chain down here. We're going to talk about false chain in a little bit. Okay, let's look at the common invalid arguments now. So we're going to switch our color coordination to red now. So same initial premise, right? This time, instead of going from left to right, I'm going from right to left. That's the converse pattern, right? If I know if P then Q, then I try to argue from Q back to P. That doesn't make sense. That's the converse, right? I'm going from the right to the left. That is an invalid argument. It's not a bad argument. It's a bad argument. And so we call it the fallacy of the converse. Okay, what does this look like? What does this look like? You're going from the left arrow to the right. But then instead of going from left to right again, you're going opposite direction. You're going against the arrow. You're going from right and trying to conclude the left. So that's what went wrong. Now, what would this look like in context of our P and Q that we chose? So this would say, if today is Sunday, then tomorrow is Monday. Okay, tomorrow is Monday. Therefore, today is Sunday. Oh, holy smokes. That sounds reasonable, right? Doesn't that sound reasonable, like a good argument? Well, you know what, guys? The argument, even though it ends up being true in the end, the argument itself is actually invalid. Isn't that crazy? Let me think of how to. Maybe I want another example that illustrates this. Actually, this is good in a way, because this really points to how we can be thrown off, right? Because this sounds legit. Doesn't that sound okay? If today is Sunday, then tomorrow is Monday. Tomorrow is Monday, therefore today must be Sunday. And that sounds like something that makes sense, but actually that as an argument is invalid because you're following the converse. No, it just so happened we got lucky in this case with our particular P's and Q's that it turned out to be a true statement in the end, but the argument itself is invalid. It's invalid. Let me see if I can think of another example. Let's use the standard one. Let's use an alternative example here for the invalid ones. Let's say P is you're a square. We'll use the square and rectangle example. And Q will be you're a rectangle. Okay. So let's look at this again. So if you're a square, then you're a rectangle. If you're a square, then you're a rectangle. You're a rectangle, therefore you're a square. And of course we know that is not true. So that points to how the pattern that we see here is an invalid argument. What about if we did it the valid argument route? What if we said, if you're a square, then you're a rectangle. You're a square, therefore you're a rectangle. Yeah, that makes sense, right? If you're a square, then you're a rectangle. You're not a rectangle, therefore you're not a square. Oh yeah, that still makes sense. Yeah. Okay, let's look at the second fallacy here. Fallacy of the inverse. So the inverse was, if I have my original P to Q, the inverse was negation P, arrow to negation Q, right? So here's the left, here's the right. Here's the negation of the left, concluding the negation of the right. So here's the pattern. Left, arrow to right, negation of the left, and then therefore negation of the right. So in context, let's look at this. If you're a square, then you're a rectangle. You're not a square, therefore you're not a rectangle. That's not always true, right? You could be this shape. It's not a square, but it is a rectangle. So you see how that argument can fall apart. Okay. Let's move on. So that's the fallacy of the inverse. How do you know it's the inverse? Because it's following this pattern, right? The negation of the left to the negation of the right. Here's the negation of the left, negation of the right. That order. Okay, the false chain. False chain is imitating the transitive reasoning, but something goes wrong. So if I look at the first part, it looks correct. P to Q, that's the same, right? And then Q to R, okay, that part is the same. So that's looking good so far. But what happens wrong after that? Well, look at the conclusion. The conclusion they made is R arrow to P. But think about this. You're going from P to Q, Q to R by my premises, right? Just now I tried to conclude R back to P, but that's the opposite way of where my arrows are going. It's going the wrong direction. So that is not a good conclusion to make. That's why it's false chain. That's invalid. That's invalid argument. And this guy over here, that's the inverse of the correct statement. Remember, the inverse is not logically equivalent, right? So the correct statement was P to R, but this one is not P to not R. So what's happening in terms of the pattern here? You're going from left to center, and then from the center to the right. But what are you trying to conclude? You're trying to conclude from the wrong direction. You're trying to go from right back to the left, and that's no good. Or alternatively, you're trying to go from the negation of the left to the negation of the right. But that's the inverse pattern. That's also not correct. So both of these would be called false chains. Another way to get a false chain is what I mentioned earlier, and that's when the center things don't match up. Okay, what would this look like in context? So let's add a third statement. Q, you're a rectangle, and if you're a rectangle, then you're a quadrilateral, right? Quadrilateral is a thing with four sides. A shape with four sides. Lateral. Okay, so what would that look like here in context? If you're a square, then you're a rectangle. If you're a rectangle, then you're a quadrilateral. And what's the conclusion? If you're a quadrilateral, then you're a square. No, that's not true. That's not true. If you're not a square, then you're not a quadrilateral. Also not true, because you could be like a trapezoid, and you still be a quadrilateral, but you're not a square, right? So yeah, we see how this kind of argument falls apart. Now, if you had tried this with the original P's, Q's, and R's, it might have seemed like it was making sense, right? But the argument itself, if you follow this false chain pattern, the argument itself is invalid. So what we're evaluating today is whether the argument structure itself is valid or invalid. Okay, guys, thank you for sticking with me. I know that was a little bit long, but you know all the theory now. You should be able to do all the questions. So before you watch any of the other videos, make sure you try out all the questions. And then the next videos come in, I'm just going to jam through all the answers.